can be somewhat of a trickier concept. So I'd like to try and simplify as much as possible. Well, I have two cases here. We're going to talk about gravity, and we're going to talk about electricity in terms of a gravitational field and an electrical field. I'm going to use uniform fields here to simplify, but these concepts apply to both non-uniform and uniform fields. If you look at the gravitational field here, we don't have one, but if we assume that this is a room, this being the ceiling, this being the floor, we should be able to safely assume that the field, the gravitational field in this room, will go from the ceiling to the floor. So if I drop something near the ceiling or let go of a mass near the ceiling, it should begin to accelerate near the floor. Similarly, with this electric field over here, hopefully by now you realize that the field will always go from a positive charge to a negative charge. So the field, my electrical field over here, should look like this. This is obviously a result of testing with a positive test charge. If I put a positive test charge anywhere between these plates, they will be forced in this direction due to the electric field acting on a positive test charge. Now, for sake of simplicity, we know that the acceleration due to gravity is negative 9.81. I'm just going to round it. I'm just going to say let's make it 10 meters per second squared to simplify the math here. Now, if I were to put a mass, let's just pick a location. I'm going to say that that location is 1 meter off of the ground. Now, that's just a location. There's not necessarily a mass there. However, if I took a mass of 1 kilogram and I were to place it at this point, well, we know we could find our potential energy by multiplying our mass times our acceleration due to gravity times our height. So if I were to do that, if my mass is 1 kilograms, we know my potential energy is going to be my mass, which is 1 kilograms, times my acceleration due to gravity, which I've rounded to 10 for this example, multiplied by the distance in meters from the ground. So if I have a mass of 1 kilogram and it's located at this point, that mass will have an actual potential energy, in this case, of 10 joules. If, however, let's say I took that same location and I plugged in a 2 kilogram mass. I took a 2 kilogram mass and I placed it right here. My height is the same. My acceleration due to gravity is the same. The only thing that's changed will be my mass. So in this case now, my mass times my acceleration due to gravity times my height, in this case, will give me 20 joules. This object, this specific 1 kilogram object, had this much specific energy when I put it at this point. This mass, which is twice as much, had twice as much energy at that same exact location. All I've changed is the actual mass. One more time, if I were to say place 3 kilograms at that location, 3 times my acceleration due to gravity times my height is going to give me 30 joules of energy. So you can see here when I plug in specific masses, I get specific potential energies. When we're talking about potential as opposed to potential energy, these are the actual energies I get. But if you take a look here, when I plug in 1 kilogram, I get 10 joules. 2 kilograms gets me 20 joules. 3 kilograms gets me 30 joules. So if I wanted to simplify this, hopefully you see that if I said that at this specific point right here, any mass that I place at that point, for every kilogram, I will get 10 joules per every kilogram that I place there. So these are specific masses with specific amounts of energy associated with them, but this specific point is always going to be 10 joules per kilogram that I put at that location. This is the potential energy we're talking about. This is what would be known as just potential. We've eliminated the actual amount of energy you get, and we've summarized this one location as giving me 10 joules at that location for every kilogram that I put at that location. It's important to realize that it's the location we're talking about when we talk about potential as opposed to the actual mass when we're talking about potential energy. The same applies over here. If I were to take a charge here and we were to say that at that location, very similarly, just like this gave me 10 joules per kilogram, we're assuming that at this point, let's say the voltage here now, the voltage, which measures our electric potential, let's say our voltage is 10 volts. Well, that's the same as saying 10 joules per coulomb. So similar to what we have over here, we know that if I place 1 coulomb of charge, well, you hopefully remember that our potential energy is going to be, for a uniform field, it's going to be our charge times our electric field times our distance of this object. So if I assume here that my electric field is going to be 10 newtons per coulomb, just to keep it similar to our previous problem. So our electric field strength here is going to be 10 newtons per coulomb. The distance we will say will be 1 meter. Well, you can see here when I place 1 coulomb of charge, my charge is 1, my electric field is 10, my distance that it's been moved, or my height here, is 1. So what I will get will be 10 joules of potential energy. When I have 2 coulombs of charge, it will be the charge. Remember, the charge times the electric field times the distance. 2 times my electric field strength times my distance. The only thing that's changed is my charge. I will get 20 joules of actual potential energy. If I place 3 coulombs there, well, Q times E times D will give me 30 joules. So again, these are specific amounts of energy associated with specific amounts of charge. So this is what we're talking about when we talk about electric potential energy. The charge that you put there will have that energy, and if you change that charge, you will get different energies. But for any charge you place at this point, no matter what the charge on that is, what you wind up with is 10 joules of energy for every coulomb of charge you place there. And a joule per coulomb is another way of saying a volt. So this is the same as saying 10 volts. So this is where our 10 volts come from. No matter what charge we place there, you will get the same amount of energy. You will always get 10 joules of energy for every coulomb of charge that you place at that point. The big thing to realize here is the potential energy is the actual energy you get from an actual mass, or the actual energy you get from an actual charge. The potential is very simply a location, and the potential will tell you how many joules of energy you will get for electricity based on charge, or how many joules of energy you will get based on how many kilograms you put there for gravity. So electric potential energy or gravitational potential energy, an actual amount of energy that you will get which is associated with an actual charge or an actual mass. Electric potential, it's the location, and that location will give you how much energy you'll get based on the amount of charge that you have at that location.